This is the 8th lecture of the course MTH 204A for section B. In this lecture, we'll talk about decompositions of actions and representations of groups. Let G be a group and X be a non-empty set, and G is acting on X, and Y a non-empty subset of X which is invariant under G. So we have a natural action of G on Y. From now on, we call this action of G on Y a sub-action of the given action. It's easy to see that if Y is G invariant, then its complement in X is also G invariant. Furthermore, if Y is proper, then its complement will be both non-empty and proper. So thus we obtain a natural action of G on the complement of Y as well. So the situation is that now the set X has now been split into two parts, and both these parts are non-empty and proper, and since both these parts are invariant under G, so thus the entire action of G on X has now been split into two subactions. So in this case, we say that the collection of these two subactions is a decomposition of the given action. More generally, if we are given a partition of X, let me remind you what it means. So whenever we say it's a partition of X, that means that first of all, each xi has to be non-empty, and secondly, for every I not equal to j, xi and xj, their intersection has to be trivial. So if this is a partition of X with each xi invariant, then if xi invariant, then we say that this family of subactions, the subactions of X on each of these xi's, a decomposition of the given action. So the situation here is as follows, that we are given a collection of subsets. We are given a collection of subsets such that which form a partition, and each of them is invariant under G. So therefore, thus the entire action has now been split into the family of subactions on these pieces. So this is what we mean by a decomposition of the given action of X. So again, let me repeat that. By a decomposition of a given action, I mean a family of subactions such that the corresponding subsets form a partition of the given set X. The equivalence of the following two statements is evident from what we have just discussed. So given an action, the existence of a non-empty proper G invariant subset, and the existence of a decomposition of the given action. If an action satisfies one or equivalently both of these two conditions, then we say the action is reducible. So you can see the meaning of, we can see the motivation behind this nomenclature, that is, now the entire action has been reduced into two parts. An action which is not reducible is said to be reducible. So we are now we will see some examples of irreducible actions. In order to before we get into those examples, I think it's better to have some equivalent characterizations of this irreducibility of actions, because that is going to be much more helpful to see the examples we are going to talk about are indeed irreducible. So the exercises that I would like to leave here are as follows. So given an action of G on X and a point small x in capital X, we consider the set of all translates of X by the group elements, and this is a G invariant subset of X containing small x. Furthermore, if E is a G-invariant subset of X containing small x, then E has to contain all the translates of X by the group elements. So thus we obtain that this is the smallest G-invariant subset of X containing X. Note that here smallest means in the sense of containment. So every G-invariant subset of X containing X must contain the collection of all translates of X. Since this is a non-empty G-invariant subset of X, so automatically we do have an action of G on this set, action of G on this set, and we are now going to see that this action is irreducible. And in fact, if the action is irreducible, then x must be this for any point x in X. So the second exercise gives us the 4 equivalent characterizations of irreducibility, that is, the action is irreducible. The second condition says that for every x, so the situation is if we choose any x inside capital X, then by translating that by various group elements, I will reach every corner of the given set X. The third condition is almost same, but here it says that if I can do the previous thing for some x, even then that's enough and in fact equivalent. So the first condition says whatever be my initial point, and the second condition says that if for some initial point if I translate that point, then I will reach everywhere. So the fourth condition says that given any 2 points, then by applying a group element we can move this point x to the point y. So these are quite it's quite clear why these 4 statements are equivalent. I leave the routine verification to you. So the this fourth condition is actually it turns out to be very useful in order to see a given action is in order to see whether a given action is irreducible or not. Okay, now we will talk about examples. Before that, I should tell you that for this action, this terminology irreducible is not standard. In literature, people rather call it transitive. But in this lecture, we will stick to this irreducibility. This is because then it will be easier for us to see the similarities between irreducibility of actions and that of representations. So for this lecture, we will stick to this terminology irreducible. Okay, so what are the examples? So for any set X, the action of Sx on X is irreducible. So again, this becomes evident in view of this fourth one in the list of equivalent characterizations of irreducibility. Now let's talk about for any x, this is irreducible. In particular, the action of Sn on 1 up to n is irreducible. So now let's talk about the restrictions of the previous action to this important subgroups, that is the action of an and d to n on this set. It's also easy to see that they are irreducible, and the action of d to n on the set of all sides of Pn is this is also irreducible. So for d to n, in fact you can convince yourself. In fact, you can convince yourself that these actions must be irreducible by by drawing pictures and by visualizing geometrically. Of course, the formal one, that is the algebraic one, is left to you. So, for example, the action of d2 on this side. So, it's easy to see that by rotating by rotations we can send any side to any other side. So, geometrically we can visualize that this is irreducible. And of course, to be formal, we have to do it algebraically. As I said, that's left to you. Okay, let's come to the third example. The third example says that for any vector space V, if we consider the action of its general linear group on that vector space, the action of GLV on V cannot be reducible, because we see that like if we try to move the origin, then certainly if we want to translate the origin, then certainly we are not going to get anything other than the origin. So we should throw out origin, and therefore we can throw it out because the non-zero vectors is also invariant under the action of GLV. So thus the action of GLV on this collection of non-zero vectors in V, this is easily seen to be reducible. Because if you take any vector non-zero, any two non-zero vectors x and y, you can show that there is a linear map which sends x to y. For finite dimensional situation, this is very easy. For infinite dimensional, you need some extra care. You may need some standard facts from set theory. So I'm leaving all this to you, assuming that you can handle. So the crux of the point is that the action of GLV on this set is irreducible, and when the V is finite dimensional, dimension is at least 2, then the action of the special linear group is also irreducible. So I would this you may take as an exercise. And for any R, the action of GLV and SLV on the collection of all R dimensional subspaces of V, that's also irreducible, because if any two R dimensional subspaces are there, then by a suitable linear map you can always so if for two R dimensional subspaces, you can by a suitable linear map you can always get that. And this linear map, if necessary, can be chosen to be of determinant 1. So this also is left as an exercise, the routine verifications. Okay, now let's come to the fourth example. So the fourth example is a rather easy one, that the action of a group on itself by left multiplication and also by right multiplication, they are irreducible. That's quite clear. Let's say for the left one, if x and y are two group elements, then yx inverse, then let me write it in this way, yx inverse x becomes y, right? Okay. And the action of G on the set of all left cosets of a given subgroup H, that's also irreducible. It is so the proof of this is same as that of irreducibility of actions of a group on itself by left multiplication. So these are the common and in fact easy examples. Later on, when we will see many more examples of irreducible actions. Okay, so now let's talk about the main content of this lecture. So in this lecture we will show that every action admits a unique decomposition into irreducible subactions. So again, let me remind what I mean, that given an action, there exists a unique collection of subsets such that, first of all, this is a decomposition, and furthermore, for each I, this is irreducible. So this is the precise statement that we are going to establish. So when x is finite, then establishing this is not at all a big deal. We can directly do that by using induction. So let me just quickly tell you the argument. So if the action is not irreducible, then that means there will be some y, proper and non-empty, which is invariant under G, and then we have x minus y. Now see that both these are having less number of elements. Both these are having less number of elements than that of x, because strictly less than the number of elements in x. And now by induction we come. Since both y and x minus y, these two sets have less number of elements than that of x, we can run the induction argument, and thus the claim is established when x is in a arbitrary finite set. Okay. So the proof is very simple, that if it is irreducible, then there is nothing to do. If it is not irreducible, then there will be a partition, and now the subsets of that forming that partition has less number of elements than that of x. Therefore, you can run induction. And thus you obtain a decomposition. To prove but in this lecture we will even prove this when x is not necessarily finite. So to prove this general case, we need to make certain observations, which will lead us to the desired decomposition. So we observe that this relation, that is x and y, these are related if and only if x can be translated to y by a group element. If we consider this relation, then this relation happens to be an equivalence relation on x, and so it's very natural to ask about the equivalence classes whenever there is an equivalence relation. So it's also easy to see that for any x, the equivalence class of x is nothing but the translates of that x, all the translates. Okay, so that's evident from how the relation is defined. So this translates we have already encountered earlier here. So this set for any x, for any small x in capital X, its equivalence class is indeed the smallest G invariant subset containing y. So it's customary to call this the orbit or trajectory of x under this given action, and denote this by OX. Since OXs are the equivalence classes, so from that it follows that the distinct orbits under this action form a partition of x. Okay, so this is just a mere consequence of that for an equivalence relation, the equivalence classes form a partition of the given set, and here the equivalence classes are nothing but the g orbits of the points. So the distinct orbits thus form a partition of x. Before we go further, let me deduce a few corollaries. Let me deduce an important corollary of this. So if x is non-empty and finite, then if we denote the distinct orbits by 1 up to OK, then since x is the disjoint union of y's, from that it immediately follows that the number of elements in x is nothing but the sum of the number of elements in those orbits. So this observation has an interesting consequence, which you might have, which I'm sure that you have seen earlier. So so this is a nice consequence which we are going to talk about. I'm sure that you have seen that earlier, but here we with us see a different, I mean not a fundamentally different proof. So another proof of that fact which I am going to talk about. So if G is a group and H is a subgroup, we consider the action of G on X by left multiplication. So recall that G acts on X, G acts on G by left multiplication. Now we restrict this group to H. So H also acts on G by left multiplications. And under this action, what are the orbits? So given an X in G, its orbit is easily seen to be the right coset, right? Now, if G is finite, this tells us that G, the order of G is nothing but the sum of the orders of all distinct right cosets of H in G. All distinct right cosets of H in G. Yes. So now again, I presume that you have already seen this. So I would like to just remind you that any two cosets, they have same number of elements, because H and Hx, there is an obvious bijection sending each Hx to Hx. So that this shows that any two cosets have same number of elements. Therefore, this yields that because in all the distinct cosets we always have the same number of elements, and that's exactly order of H. So therefore we obtain that order of G is some positive integer times order of H, or in other words, order of G divides order of H divides order of G. So this is called the Lagrange's theorem. So thus we have arrived at a proof of Lagrange's theorem from the point of view of group actions. Now let's get back to our main content. So if for a general action, so now okay, so here also we will assume that X is finite. Here also we'll assume that X is finite. So now look at this orbit. So some of these orbits might be trivial. That is, what I mean by trivial is just a singleton. So the orbit of X is singleton X, is same as saying that so this only happens when so orbit of X is singleton X if and only if for every G in G Gx equals to X. So that is, the point is fixed under this action. So therefore what we have just observed is the trivial orbits in this list, they do correspond the fixed points under this action. So now if necessary we may relabel all the non-trivial orbits in this list. If necessary we may relabel them like this. And therefore now from this formula we obtain this, that number of elements in order of X is, of course, like earlier, we have to consider the sum of the orders of each non-trivial orbits, and together with that we have to consider the trivial orbits. So we are just rewriting this, we are just breaking this right hand side into non-trivial and trivial part. So this is the non-trivial part, and the trivial part, as we have already seen, that the trivial orbits do correspond precisely the points which are fixed. So this is the fixed set of this action. So thus rewriting the previous formula by splitting the right hand side into trivial and non-trivial, the trivial orbit and non-trivial orbits, we obtain this. This is known as the general form of class equation, which we will. So the class equation in the context of action on finite sets is a quite important concepts, and this happens to be instrumental in several proofs, instrumental in the proof of several results in finite group theory, which we will encounter very soon. All right. So now so this is all. We obtain when the set is finite. Now let's get back to the main question which we are dealing with, is the decomposition of an action. So let G acts on X, and C be the collection of all these distinct orbits under this action. So now remember that since C is nothing but the collection of all distinct orbits, so indeed C yields a partition of the given set X. And since each orbit is G invariant, and already we have seen that the action of under the action, the subaction of the group on any orbit is irreducible. Hence, from all this we obtain that this is a decomposition of the given action into irreducible subactions. So let me quickly summarize. So when X is finite, then we don't need to get into orbits. We can directly prove that using induction, but we want to prove that in generality. For that, we define this equivalence relation, whose equivalence classes turns out to be this set which we have encountered earlier. And so this, for any given S, this subset is called the orbit of X. Now since these are the equivalence classes, so distinct orbits from a partition of X, and the action of G on any orbit is irreducible. Therefore from this it follows that this is a decomposition of the given action. So thus we have proved that given any action of any group on any non-empty set, then that action can be split into some irreducible subactions. Okay. Remember that when X was finite, then this partition has to be finite, but otherwise this need not be finite. This C could be a huge collection. So what we have done is we have given an action of a group on a set. We have split that action into many irreducible parts. That's all we have done so far. Okay. As I have already said that whenever we define something for actions, or we prove some theorem for actions, it is very natural to look at their analogues when the action is by linear automorphisms, that is when we are having representations. So this is what we are going to do now. So the decomposition of actions which we have just proved, we are now going to see its version for representations. But in case of representation, since we have the linear structure in the picture, we need to modify the meaning of invariant we need to modify the let me put it in this way, that for general actions we can take invariant subsets, but for representations we have to modify that to invariant subspace. So similarly, for a general action, when we talk about its decomposition, that means we can just take a partition into G invariant subsets, but certainly that's not a good choice when we are dealing with the representation. Instead, we have to consider instead of, because even if considering just the yeah. So even if we consider partition V into G invariant subsets, still those subsets may not inherit the vector space structure. So instead of considering set theoretic disjoint union, rather we have to what we have to consider is we should look for decompositions of V into G invariant subspaces. Okay, that's the most natural thing. We just here cannot simply take set theoretic union. So let me remind you that so let me first define the meaning of irreducibility in the context of actions. So as I said that here we cannot just take G invariant sets, we should insist that it has to be a subspace, and since for any representation these two obvious subspaces are always G invariant, so here by irreducibility we mean that by irreducibility we mean that there doesn't exist any subspace other than these two which is invariant under G. That's what exactly means by the irreducibility of the action. So let me give you some examples of irreducible. So yeah, it's a irreducibility of representations. So let me give you some easy examples of irreducible representations. The first example is if the dimension of the representation is 1, then of course any because any action of any group on any vector space of dimension 1 has to be reducible. The second example is the following representation of this dihedral group. So yeah, I would like to leave this as an exercise that this representation given by sending R to this matrix and rho to this matrix. So this is a representation of this dihedral group on C2, it's left as an exercise to you that this representation is indeed irreducible. And next we talk about another irreducible representation. It's the representation on the same vector space C2, but here the group is the group of quaternions. So this actually this representation is also irreducible, which you may take as an exercise. Okay, now let's come to the one of the main theorems. So before getting into the theorem, let me again tell you that when in the context of general actions, we see that the existence of a G invariant proper G invariant subset is same as the existence of a partition of G into two non-empty and proper subsets, which are proper subsets, both are invariant under G. So these two things are equivalent. But in case of representation, we should always expect something like this. But here, as I said, that instead of considering just set theoretic union, rather we should go for decomposing V into the direct sum of two non-trivial G invariant subspaces. So this theorem basically talks about that. So you can regard this theorem as the analog for representations of the equivalent criterion for reducibility, criterion for reducibility for general actions. So here this says that if we are given a vector space and G be a finite group, so finiteness is actually required here. So if it is a finite group and there is a vector space such that we have a representation, then for any G invariant subspace W, there must exist another G invariant subspace W prime such that V equal to W direct sum W prime. So if you remember from linear algebra that these subspaces are called complementary subspaces of W. So in view of this terminology, you can read the statement in this way that every G invariant subspace admits a G invariant complementary subspace. Okay. Before we begin the proof of this theorem, let me remind you some facts from basic linear algebra, because we are going to use them in this proof. So recall that for any given vector space V and any subspace W, if W prime is a subspace such that V equal to W dx some W prime, then the operator that sends each V to its component in W is a linear operator from V to V with these two properties, that is P square is P and the image P is W. So whenever we here V, so if we are given a vector space V and a subspace W, then whenever we find, so if now again let me again say that from the beginning, that is if so suppose that we are given a vector space V and subspace W. If W prime is a complementary subspace, then automatically we can find a projection operator from V to V such that, so by a projection operator I mean operator from V to V satisfying this property. So if W prime is a complementary subspace of W, then immediately we obtain a projection operator on V whose image is W. Conversely, if we are given a projection operator P on V satisfying if we are given a projection operator P on V whose image is W, then it's easy to see that if we consider the kernel of that projection operator, then V happens to be the direct sum of W and the kernel. So again let me repeat. So earlier we have seen that for given V and W, then for every complementary subspace we obtain a projection operator whose image is W. Now what we have seen is for every projection operator whose image is W, we can produce a complementary subspace of W. Now I would like to leave the following for your verification, that these two observations immediately guarantee that the complementary subspace of W are in bijective correspondence with all the projection operators with image W. That's what we have seen, that from a W prime I can construct a projection operator, and then from any projection operator I can construct as a complementary subspace. So it's just you just have to make sure that these two processes are inverse to each other, which I am leaving to you. So the upshot is that from the above it follows that the collection of all invariant in the collection of all complementary subspaces W and the projection operators whose projection operators having the same image W are in a bijective correspondence. Exercise. So let me be as above. Then for any, again try to understand the situation. So far we have seen that given any W, if W prime is a complementary subspace, then automatically we obtain a projection operator. Okay. So this exercise says that given any W, there indeed exists a complementary subspace. So for finite, when V has dimension finite, then this is easy to see. You just start with the basis of W and extend that. When V is infinite, then you have to do some work. In fact, that gives you proof which holds in generality independent of the dimension of V. So what you do is you consider this V mod W. This is a vector space. So this vector space has a basis. Because I'm sure that in a simple application of John's lemma, so whenever you have a basis here, you just consider their pullbacks inside V, and those pullbacks are going to span a complementary subspace of W in V. So when for any vector space V and any subspace W, indeed there is a subspace which is complementary to W, and in view of the equivalence that we have seen a few minutes back, we can say that this equivalently we do have a projection operator whose image is W. So I repeat, that's what we have proved is for any vector space V and subspace W, we do have a projection operator. So please try to understand what is going on. So earlier we have seen that if there is a complementary subspace, then there will be a projection operator and vice versa. But in order to guarantee that there is a projection operator whose image is W, that's not yet guaranteed. So in order to guarantee that, we observe that for any W, always there is a complementary subspace. And then from in view of the previous discussion, it immediately follows that whatsoever W is, there is always a projection operator whose image is W. We use these two in the proof of the theorem. So what we are supposed to prove is, so here W is given a G invariant subspace or G invariant subspace of V. We are supposed to find a G invariant subspace W prime such that V equal to W direction W prime. So if we set aside G invariance for the time being, then of course we can construct a W prime such that this happens, but this W prime may not have the G invariance property, right? So in view of the equivalence that we have just stated, so we do have a linear operator, we do have a projection operator whose image is W. Okay, so we do have a projection operator whose image is W, and we have already seen that. Again, let me start the proof from the beginning. The exercise says that for any V and W there is a projection operator. This is exactly what we are using. So there is a projection operator P, and we have already earlier seen that if V is a projection operator with image W, then V must be W direction kernel P. So but this may not work in the context of in the proof of our theorem, because there is no guarantee that this complementary subspace is going to be G invariant. I repeat that we can find the complementary subspace, of course, namely from the projection operator we can find a complementary subspace, but the problem is this subspace may not be invariant under G. So let's try to see what are the obstructions. For the obstructions for this be obstructions, so that this what are the obstructions for this to be G invariant? Let's first see that. So that's actually easy to see that if we take X from the kernel of P, and we want to show that rho Gx also lies in the kernel of P, so that means we have to show this is 0, but there is no guarantee that this is going to be 0. But however, we can observe that if we can write this, that for any G, P compose rho G, if we can guarantee this, if we have this, then certainly this will imply this, then we will be done. So this is equivalent to say that rho G inverse P rho G is going to be P for every G. So thus we see that if the operator P, projection operator whose image is W, if this operator is invariant under all the conjugations, then we will be through. Okay, because then from this we can immediately switch rho P and rho G, and that exactly gives us what we want. But so therefore everything is now dependent upon whether this P is invariant under all the conjugations of or not. But in general, there is no hope that the P, so this P has been obtained from this exercise that which says that there is some P. There could be other P's, of course. So from this very previous existential argument, the P that we have, there is no guarantee that this is going to be invariant under all the conjugates. So what therefore we will do now is, from this P, whatever be that P is, I don't bother about what that P is exactly. So what I am going to do is, from this P, we will construct another projection operator, say P naught, whose image is also W. And this projection operator P naught is invariant under all conjugations for FDG not in FDG in G. So this is what we are going to do, that from the projection operator P we are going to define another projection operator whose image is same W, and that operator is invariant under all the conjugations. So that gives, if we once we do that, we see the proof is over, because since this the P naught has image W, since this projection operator P naught has the same image W, so then we can write V to be W plus kernel P naught. We can write V like this, and as we are already convinced that if the projection operator is invariant under all conjugations, then this subspace will also become G invariant. So now our task is to define the appropriate P naught. So since P naught has to be invariant under all the conjugations, so keeping that in mind, what we do is we consider all possible conjugates of P, and simply we average that. So we consider all possible conjugates of P, then take their sum, and then divide it by the order of the group G. So here we have used the group is finite. So the reason for choosing this scalar will be immediate, but the main part is this. So the sum has to be taken, because otherwise one cannot guarantee that whatever we are going to do is going to be invariant under all the conjugations. So since we have considered all such sums, we can immediately see that this operator is invariant under all conjugations. So we will now see. So let's now go step by step. So the linearity of P naught is not an issue. Observe that if W is in W, then if W is in W, then P naught W is also equal to W. This is because PW is W. Okay. So therefore here we will get P naught W. This gives me this. And now we remember that we have this scaling factor. So therefore P naught W is W. So thus this shows that W is in the image of this linear operator P naught. Okay. Now on the other hand, we see that for any V, P naught V is the sum of all these. Now since P is there and the image of P is W and W is G invariant, it happens that all these summands are in W. So therefore we see the image goes inside W. So I repeat, so this is for the first is rho G inverse V. So this is certainly inside W for any V, because the image of P is W. Now furthermore, when we operate rho G here, say from the G invariance of W, it goes inside W. So thus now we see that the image of P naught is contained in W. A few minutes back we showed that W is contained in the image. So from this it follows that the image of P naught is W. Okay, the image of P naught is W, and W and P naught fixes every point of W. From this it is clear that P naught is a projection operator. Okay, because it fixes. So because P of P naught of P naught x, since this is in W, so it has to be P naught x. So P naught happens to be a projection operator whose image is W. Hence, as we have already said while considering P naught, that once this operator is a projection operator whose image is the same W, then we do have that the kernel of P naught is an invariant. If kernel of P naught is a complementary subspace of W, that is V equal to W plus W prime. Now we do the final stage. Now we will come to the final stage where we have to show that this W prime is G invariant under G, and that will be just a straightforward one, because the way this P naught is defined, so that takes care of all the conjugations. And since we have taken the sum, so now it is in P naught is invariant under any conjugation. So that is because of we have considered the sum of all possible conjugates of P. So now let's do the formal verification. So for any x, so this happens to be this. Now since x is fixed and G runs over all elements in G, so therefore these are basically all the elements of the group itself. Hence, this happens to be P naught only. So this finishes the proof of this theorem. I would like to give another proof of the same theorem, but to a restrictive case, that to a restrictive case, that is, if the field is C and dimension V is finite. In this situation, I would like to show you, give you another proof of this theorem. Please note that so here V need not have dimension finite, or the bottom field need not be C. But when the bottom field is C and V is having finite dimension, then we can prove this in a different manner. So what we can do is so let me put them as exercises. So the first exercise says that if we are having an inner product space over R or C, and is a representation of G on the inner product space V, such that each operator rho G is orthogonal or unitary depending upon whether the inner product space over R or C. So what I mean by this is it preserves the inner product. So if we are having an inner product space over R or C and a representation such that each rho G preserves the inner product, then for every G invariant subspace, its orthogonal complement is also going to be G invariant. That's a direct verification, as the inner products are being preserved. So as an example, in the action of Sn on Cn, we see that this vector E1 up to En is in this action, and subsequently, of course, in the representation of Sn in G, in the representation, we see that this subspace is invariant under Sn. So therefore, we obtain that this subspace, that is the complex hyperplane, is also invariant under Sn. So let me again repeat that consider the representation of Sn, the representation, standard representation of Sn. So we so which is same as saying that Sn, considering the action, standard action of Sn on Cn, we see that this is a vector fix. This is a fixed vector, hence the subspace is invariant under Sn. And in this representation, corresponding to each sigma, the matrix is nothing but a permutation of the columns of the identity matrix. Hence, it's already unitary. So, since all these matrices are unitary, therefore, automatically inner product being unitary is same as the inner products are preserved. So, thus, since this is a invariant subspace, its orthogonal complement is also going to be invariant under Sn. And the orthogonal complement of this is easily seen to be this complex hyperplane. The second exercise says that if we are given a finite dimensional vector space where a finite group is having a representation, then we can define an inner product on this vector space such that this happens. Okay. So let me explain the exercise once again. So we are just given a finite dimensional vector space where a finite group is having a representation. Then we can make V an inner product space in such a way that each of these operators will be orthogonal or unitary. And now combining the first and second exercise, we can conclude. Combining these two, we can give an alternative proof of the theorem in this situation. So I am leaving that to you as an exercise. So I think already you have got the idea that what you have to do is you first have to put an inner product appropriately. That will be given by the second exercise. Now once that is there, then you consider the orthogonal complement of the given subspace W. And the first exercise guarantees that it's G invariant and the decomposition is obvious. Okay. So the corollary of the theorem, one immediate corollary of the theorem is as follows, that the following are equivalent for a representation of a finite group. So what are equivalent? That rho is reducible, that is not irreducible, that is there is a proper non-trivial invariant subspace. And another equivalent way to say that is there exist two non-trivial G invariant subspaces such that V can be decomposed into the direct sum of W1 and W2. So you see that you can immediately realize that this is the version of equivalence of reducibility for general group actions, which we have seen in the beginning of this lecture. So this is the version of that in the setup of representations. And here also I would like to leave another exercise to you. So I think this not Z, yeah, so Z1, Z2, Z3. So the exercise is already we have argued that the representation of S3 on C3, of course it's not irreducible, because the subspace by E1, E2, E3 is a one-dimensional subspace which is invariant under S3. So now we look at this invariant, its orthogonal complement. So thus S3 has an action on this hyperplane. S3 is in fact a representation on this hyperplane, and this sub-representation is irreducible. That is what is this exercise about. Alright, now let's come to the decomposition theorem for representations of finite groups. This is known as the Maschke's theorem. It says that so this theorem is nothing but you can regard that as the version of as the verse analog of decomposition of of action into irreducible subactions, so which we have proved in this lecture earlier. So this Maschke's theorem is the analog of that in the setup of representations of finite dimensional representations of finite groups. So it says that if G is a finite group having a finite dimensional representation, then there exist subspaces, G invariant subspaces, such that V can be written as a direct sum of W1 to Wk, and one cannot further decompose that. That is, the sub-representations on each of these Wi's is the sub-representations on each of the Wi's are irreducible. So this is actually a statement about complete reducibility of any representation of any finite dimensional representation of any finite group. It just says that given any finite dimensional representation of any finite group, then one can find G invariant subspaces such that V can be decomposed as a direct sum of those subspaces, and of course those subspaces, all of them will be G invariant. So those sub-representations cannot be reduced further. So that is, they are all irreducible. So the proof of that is actually the strategy of the proof is exactly same as that of decomposition of an action on finite sets, which I have already mentioned in the lecture. So what you do is, if the given representation is irreducible, then you simply stop. Then you don't have anything to do further. Otherwise, in view of this equivalent criteria, you know that there exist two subspaces in non-trivial subspaces such that both are G invariant, and this decomposition holds. Now it is clear that both dimension W1 and dimension W2 are strictly less than dimension V. So therefore the representations of G, or the sub-representations of G and of G on GLW, on GLW1 and GLW2, we see here in both these cases the dimension of the vector space has been decreased. Now you run an induction argument, and this completes the proof of this. This completes the proof of Maschke's theorem. All right. Well, I just noticed that I forgot to mention one thing. So let me go back to the proof of the decomposition for general actions. So we proved that given any action, this is a decomposition into irreducible subactions. But we forgot to say why this is unique. That's quite clear, because if we are given any decomposition, we don't know whether that's into orbit or not. If we are given any decomposition of the given action, now what we do is for each O, for each O belonging to this collection, pick any x. Now it's easy to see that O has to be orbit of x under the action. So therefore it shows that if we are given any decomposition, then the corresponding invariant subsets must be all the orbits under this action. So when we are talking about decomposition of an action, then this decomposition of an action into irreducible ones, irreducible subactions, then this decomposition happens to be unique. However, for representation, this is not the case. So one can produce one can have different set of G invariant subspaces such that all the corresponding subrepresentations are irreducible. So we will see that later on. In fact, let me give you a very trivial example for that. So, for example, if we just consider, let's take let's say any group, it doesn't matter. Let's say Z mod 2Z. So we consider this action on C2. This is let's take the trivial representation. Let's trivial representation. Then C2. Then since the representation is trivial, so every subspace of C2 is invariant under Z mod 2Z. So now whatever decomposition you consider, whatever basis of C2 you choose, V1, V2, whatever basis you choose, you see that this is a decomposition of the given action into irreducible subactions. Whatever V1, V2 basis of C2 we choose, this is going to give us a decomposition of C2 into irreducible subactions. Okay. Why irreducible? Because the action is trivial. Then since the action is trivial, then therefore any subspace is invariant, and this subspace has dimension 1. So therefore the subrepresentations on these subspaces cannot be reduced further. So this trivial example shows that in case of representations, certainly this choice of W1 to WKs, this set for the W1 to WK is not actually unique. Okay, so with that I will finish this lecture.